So what is computational science, or how is it also called scientific computing? Computational science is not a single course, it's not a single discipline, it is a large field, much like, for example, electrical engineering, that encompasses a lot of different methods, tools, and actual applications. So why will someone do that? What do you need from your computer, and why is it beneficial to run things in such a way? In previous years, before the advancement of electronics and the appearance of computers, if you wanted to do science, you had to do a lot of manual calculations. Whenever you wanted to conduct a physics experiment, you would take your object of interest and take some measurements manually. Then you would manually record them, and then you will take the data. After that, you would process it with some statistical methods scientists developed long ago before computers appeared. And then you will try to find some correlations and derive some laws. And there was no other way to do it. You either had to conduct your experiments yourself or observe things that were happening around you. For example, when people were looking at stars and planets, they figured out that this planet was at one location, some time after it moved to another place, and they would record those positions one by one with some precision. And then they constructed models that were trying to explain how and why those planets moved. And it turned out that those models were good not only in their interpolation of existing data, but also in that they could extrapolate new predictions from them. And this is the reason for doing science. So you do measurements and then you build a model. And if the model is so good and makes predictions beyond your actual measurement points, then you succeeded. It was complicated because manual calculations are not fast and people are prone to making errors, though they had to double and triple check the outcomes. Thus people were thinking about looking for a way to remove the need to do the actual calculations manually. And once we have figured out some mathematics that allowed us to create a computer as a concept, we have managed to implement those computers first in mechanical implementation, and then electromechanical implementation, and nowadays they are purely electrical. And maybe in some 50 to 100 years we will be heading to mass use of quantum computers. Though the whole point of computers' existence is to compute things. And if you apply the scientific method by using a computer to crunch some numbers, you technically do scientific computing even if you don't realize that. Computers will not do modeling for you, computers will not invent experiments for you. Computers will not remove any creativity from the scientific process. What they will do is simplify your life in this one crucial aspect. They will replace the need to compute things manually. And by doing that, they enable many possibilities for science. For example, it would have been impossible to run considerable optimization and huge calculation problems with manual computations. And even if each person in the world would do arithmetics for a single problem non-stop, the combined computational power will still be slower by a factor of 100 or even 1,000 times compared to what your current desktop computer can do. And modern scientific computing relies not on desktop computers. It relies on supercomputers, clusters, and data centers. So now let's discuss a little bit what problems can be solved with scientific computing. One of the oldest applications that have been in use continuously since it was invented is weather forecasting. Weather forecasting models are very complex and they can benefit from increasing spatial resolution tremendously. We use a model for air movement computed on a mesh consisting of air volumes for this application. Let's say that our air consists of cubes with a side of 100 meters. We can also scale it up or down. If we increase the model's resolution by scaling the grid down to cubes with the side of 10 meters, the precision of the model will go up. I don't know what scaling for accuracy is precisely for those models in terms of dimension, but it's a computational effort that we can discuss. It will scale up by a factor of 1000 because we will have 1000 smaller ones where we had one large cube. So to get some increase in quality, you will need to put a factor of 1000 effort. Such model behavior means that you will always have demand for larger machines and larger computers and larger systems capable of computing more and more of those blocks. Also considering that the problem of computing weather is parallel. So you can take modeling into individual regions and communicate only the data between the nearby areas. For example, the weather in Moscow will not be directly and immediately affected by the weather in New York. They will interact eventually after several days, maybe even weeks, and they will do that through a chain of different blocks, but they will never interact directly and thus they can be decoupled. And for example, the Finnish Meteorological Institute uses great XC30 supercomputer with 6840 computational units. Its total peak capacity is 70 teraflops. 1 teraflop is 10 to the power of 12 flops or floating point operations per second. One operation is one division, multiplication, or addition executed by the processor. To put this into perspective, a new high-end desktop with 16-core CPU will offer about 1.4 teraflops. What are the biggest supercomputers in the world? There is a list of the top 500 supercomputers in the world. You can find this list at http://top500.org. It is constantly updated as new ones go into operation. And as of June 2021, the largest supercomputer was the Fugaku supercomputer in Japan. Its performance is 440 petaflops, or 440,000 teraflops, measured in linear algebra problems. It consumes about 30 megawatts of power and has 7,630,848 cores. That is a tremendous amount of computational power, and it is distributed, so you cannot run a single program that will use all those cores at once. Instead, you need to design a parallel solution that will also communicate different pieces of data across the interconnecting network. This supercomputer, for example, has been used in research of human breath airflow modeling and how it is affected by people wearing or not wearing masks and face shields. Fugaku is one of the supercomputers which is a large data center, and all its parts are located in the same place. Distributed cloud computing software is an alternative approach. There is a research project called Folding at Home, where people were effectively voluntarily performing scientific computer on their graphics cards. This project has been powered by Boeing software, which stands for Berkeley Open Infrastructure for Network Computing. Boeing is open source software that anyone can use. You can download it and run your own cloud computation system, so long as you have computers. The infrastructure consists of a workload server that distributes workloads and receives results, and clients that are general purpose and can download the necessary modules. The idea is that these clients and information about the workload service are available to general public. So everybody has the opportunity to download and install these and join the cluster to donate their computational resources. The combined performance of computers in this project has been around 1 exaflops or 1000 petaflops. So this distributed network was more than twice more computationally powerful than the best existing supercomputer. Other applications may not be as massive, but they are still critical. For example, NASA has its own supercomputer that is ranked 70th on the top 500 supercomputers list as of 2021. And it has computational power of 5.9 petaflops that come from about 240,000 cores. It consumes 4.4 megawatts of power, and it is primarily used for the agency's internal projects. For example, scientists might use it to compute the trajectory of a spacecraft, as gravitational problems are not linear, and solving n-body problems analytically is impossible. We must use numerical methods. In Finland, the best supercomputer called Mahti ranks 80th in the top 500 list, has 169,000 cores, and is slightly less powerful than NASA's supercomputer. It has 5.3 petaflops of computational power, and it consumes 7 megawatts of electricity. It is operated by Center for Scientific Computing of Finland, or CSC. Mahti's resources are available for public use by scientists in Finland. Hence, so long as you have a valid research project, you can apply for a share of computational resources, and you can run your project there and get the results and publish scientific research from those results. They don't have to pay for that. Anything that's on that computer is a resource that is granted to researchers by Finnish government. What is the essential part of these problems? A precisely defined numerical model is a key for computational science, because your results will only be as close to reality and will have as good a capacity for extrapolation as the quality of your model. The model needs to be based on existing knowledge of the underlying phenomena derived from physics. The second property of those problems is that they all have a considerable number of input parameters. For example, we might have 100 variables that go into our model. They might define some geometrical properties of the object studied. And let's say we are looking for the best combination of those 100 parameters that will provide us with the best properties or the most cost-efficient solution. It doesn't even have to be 100 parameters. It can be just 2 or 3 parameters, but the problem might be very nonlinear. For example, if you will have a problem where your solution jumps all over the place, and that might be the case if you have a lot of local minima, and you want to have to find the global minimum. It would not be easy because you will have to start your search from multiple points simultaneously. With distributed and parallel systems, such simultaneous searches can run independently. What other applications exist for clusters? Not all of them follow the same approach as I have outlined above precisely. For example, you can frequently hear about artificial intelligence progress and so-called machine learning, or ML. In machine learning, instead of a physics-based model, they will use a very general-purpose model, for example, a neural network. The model can be different, and researchers can make it based on a linear decomposition of matrices. It can be constructed using neural networks, or it can be built with fuzzy logic. It can be any general-purpose model that is not derived from physical properties of the subjects that this model will represent. With any of these approaches, your model might be a representative interpolation of the input data set. However, in most cases, it will not correctly extrapolate the results outside the domain in which you defined your input set.